Okay, so I clicked stream when I was supposed to record on OBS. So let's go over this again. This is a presentation for the final of Miss Markley's data structure class at OTC CSE 210 at 2026. Data structure is a deliberate way of arranging data in memory so that it is used efficiently, not just storage. And it's a way to store storage with like a strategy. If you don't know prior knowledge of data structures, you may think that lists and arrays are basically just generic ways of holding data, and all you know is you just store data and you access it. Well, data structure is actually going to give you the back end knowledge of what's going on and different use cases on having applications that are more efficient. So why does data need a structure? Every program stores data differently using different algorithms in order to maintain the most optimal use case and storage. Picking the wrong data structure is like using a dictionary to find what departure you're in. It's technically possible, but it's very poor and unoptimal. The study of data structures is essential in computer science because it gives us comprehensive knowledge of logic for data management. It allows us to know what storing methods are best for the application we are making, along with having alternatives that use resources efficiently. So we'll go over queues, we'll go over like prioritized trees and all sorts of other stuff. So, complexity analysis. Complexity analysis is basically like the efficient use of time and storage. So it's going to have time complexity and space complexity. Time complexity, that is the amount of time it takes to do processes in like proportion of how much size is in your like storage basically. And then space complexity, that's going to be how much storage it takes to actually do your processes. Here we have time complexity. Time complexity is a measure of time which it takes in order to do an operation as more data is present. It's usually expressed with big O notation, and this is essential for evaluating data structures because the choice of data structure is significantly impacts the time complexity of operations like insertion, deletion, and search. Space complexity. This is a measure of memory space which algorithms use when executing an operation, also expressed using big O notation. Developers choose between structures like arrays and linked lists based on their overhead. And for instance, arrays often consume less space than linked lists due to the latter's pointer ahead, making arrays preferable when memory is constrained. Linear versus non-linear data structures. In a linear structure, each element has exactly one predecessor and one successor, except at the ends. The data forms a sequence, you traverse it in one direction or two if doubly linked. Think of that as your arrays and your lists currently. Advantages: simple mental model, easy to iterate, predictable memory layout, and it's got great cache locality. Some disadvantages, though, is searching is often ON, which means inserting it's gonna mean searching at whatever index you need to is going to be very tedious, like along the way. Okay, here's nonlinear data structures. It allows one element to connect to many others. The data forms hierarchies or networks, not sequences. You can't traverse with them with a single loop. You need recursion or a queue stack to manage the traversal state. The advantage is the model complex relationships directly. They enable O, log, and search. Graphs can represent anything with connections, roads, dependencies, and social links. And the log part, that means that even if they split, it's only one step for every time they need to traverse downwards or upwards or whatever. Disadvantages: higher implementation complexity, because you are going to be using a lot more memory when you are basically making a bunch of these branches in your data structure. And this is going to increase the memory overhead from their pointers. Their cache performance is often poor because the nodes are going to be scattered when you do that. Alright, here we've got arrays. Arrays are contiguous blocks of memories holding elements of the same type. Each element sits right next to the last. No pointers, no gaps. You just access each element instantly by the index, and the address is just the base plus the index and size. Simple index base loops. Arrays have a executional cache locality because the elements are contiguous. The CPU prefetcher loves them, and you can also traverse backwards or just jump by straight for things like 2D arrays stored in row major order. So access by index 01, because that it uses mathematical addresses, it is going to be one step every time it does this. Search, however, that is ON, and that means it is going to have to do a step for the range that you order for the operation. So if you want 1, then excellent, that's the worst case. The best case, it grabs the very first one. However, if you need 3, it is going to have to step 1, 2, 3, and even longer. This is how you could probably see that arrays are not the best for when you need to do search operations. They're typically when you just set the static data and then you just access it directly by the index. You can also search in them using binary search, which is an improved method that rather than just doing linear. And that what that means is it's going to divide and do a hotter colder kind of method where, say, there's 1 to 10 and you're trying to search for 3. It is going to jump to 5 and it's going to find that 3 is shorter, so it's going to go to 2, find that it's larger, and then it's going to bounce, and then it's going to find 3, and that's where you get that log n complexity, where it basically just branches and does a logarithmic hop whenever it needs to search for something. Here at arrays, inserting into arrays is also really simple because address-based indexing, it just insert directly at the end. But yeah, in the middle, if you need to insert in the middle, you again have to step through to that place and insert it. Same with delete, step to that place, insert it. Arrays, their best cases is you just have static data and you just want to access it by index. Here we've got linked lists. Linked lists are a chain of nodes holding a value and a pointer to the next node. There's no guaranteed contiguous memory. Nodes live wherever a locator puts them. The list is defined purely by pointers. A double linked list adds a previous pointer for backward. It's transversal. Transversal is you start at the head, and then you follow the next pointers until you meet the null, which is a tail. No random access, you must simply just walk the chain until you meet whatever you're trying to look for. The double chain list exists, so you can walk backwards. Circular lists, they can loop in a circle, and this is really handy for if you just want a looping list, or if you want to insert you want to have a lot of insert operations in a list, but you usually want to access stuff one at a time. because the access is by index is O of n, so that means it's going to step through each single node for everything it looks for. Same with search, and with sorted binary, it is just going to hop to whatever tail it is going to. And at the insert, it can insert at either ends, but if you want to insert something in the middle, it's got a step through each one and then insert it like the nodes. If you want to delete something, that's also very quick because, well, it's quick if you want to delete something at the start or the end, because those are just accessible from the start. But yeah. Here we've got stacks. This is a last in, first out collection. You can only interact at the top of the stack, push, pop, and remove internally. It is just an array or linked list with a restricted interface. The constraint is the point. It enforces a specific access pattern. Stacks aren't meant to be traversed. The whole contract is you see the top and you need to iterate over the stack. If you're using the if you need to iterate over a stack, you're probably using the wrong structure. In practice, transversal means popping everything off. Destructive by design. So think of like an undo button. The more changes you do and you undo, it's just gonna reverse that thing you've just done. So you add one thing, another, and if you want to remove it, you pop, 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 push, 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 pop, pop, pop. If you need a peek, you can just look over once. If you need a search, you need to go over each single node and then find it. And that's pretty explanatory over here. You just push, pop, peek, or you can search. Here we've got the vice versa of a stack, and this is a queue. This is a first in, first out collection. You unqueue at the back and dequeue from the front. The circular buffer implements this efficiently in a fixed memory by wrapping the indices around. Priority queues extend this. Dequeue returns the highest priority element regardless of the insertion order. Like stacks, queues don't support random access by design. Transversal means processing the elements in arrival order. You drain the queue. In BFS, you unqueue neighbors and dequeue at the current node. The queue naturally enforces level by level exploration of a design tree. So yeah, you NQ, you NQ, you NQ, you N. So you NQ, and you can also DQ, which means you remove the ones that you've added in order, basically. If you need a peek, you just read the front. If you need a search, you need to keep searching for the ones that you just added. And yeah, pretty explanatory. You mainly just want to access, remove, or read the very first element. And if you want to search, you just go through each element and step until you find the one you're looking for. Here we are now going through the very search efficient data trees, but they are very space complex. This is binary trees. They're a hierarchical structure where each node has the most two children, left and right. A binary search tree adds ordering. Everything in the left tree is smaller than the node, and every is smaller than smaller than the node. Everything on the right tree is larger. This is a constraint what makes efficient search possible. So at the top, you'd have like an in-between number. At the left, you'd have the smaller numbers, the right, the larger numbers. The search, it would have to start at the center. You'll check if it's less than or if it's larger than. If it's less than, if it's larger than. If it's less than, is it larger than? And this makes searching very much more quickly because it's storing it logarithmically. And this also makes all of the operations logarithmic. Because, yeah, it's just a logarithmic pattern where it checks the sides and then it just vice versa all the way down. The worst case you can really have with this is that it constantly goes long down way, like pointlessly checking the sides, and that's what the worst case of searching or doing any operation would be in a binary tree. Here we have binary tree or balanced trees. Balanced trees, a BST that enforces a height constraint. Typically, no path from the root to the leaf is more than roughly twice as long as the other. This prevents degeneration into a linked list. That one issue that I was talking about before, where it can just make a very long branch, and it makes the basically all the operations like unproportional with the data. Common types include AVL trees, strict height balance, and red-black trees, looser but faster to rebalance. Same as binary search trees in order, pre-order, post-order, level order. The difference is purely how the tree maintains itself, not how you walk it. Since it is always balanced, traversal paths are bound at O log and depth. So that means that they won't make a long path, but they will rather be kind of just. It'll try to make it a very symmetrical, like pyramid shape, whereas the previous one, it can look like a bunch of roots basically as it gets more complex. Here we have treeps. A treep is a BST and a heap simultaneously. Each node stores a key, satisfies a BST ordering, left key smaller, right key is larger, and a random assigned priority satisfies heap ordering. Parents' priority is greater than children's. Same transversal methods as any BST. In order gives sorted keys the heap property on priorities. Doesn't affect how you walk the tree. It only governs the structure shape. Treeps rail power. The treeps rail power is its split and merge operations, which allow you to divide and combine the treeps in O log n. Useful for range queries and interval problems. Search is O log n, same as BSD. You compare your target against each node's key, go left to right until you find it. The random priorities keep the tree balanced on average so its height stays around log n. When you insert, it's O log n, because when you insert a new node like normal BST using the key, then assign it a random priority. If that priority violates the heap property with its parent, you rotate it until it doesn't. The rotations are what keep the shape balanced. When you delete, you find the node, rotate it downwards until it becomes a leaf, and then you just remove it. The rotations again are bound by the height. Splitting and merging. You can cut a treep into two treeps at any key value or combine the two treeps into one. These operations are powerful and cheap because of the balanced shape. The personal application I have is that in a project I was working on called Note Etcher, I was making a game engine that is very simple and very minimal when it comes to designing rhythm games of different sorts. So here's a service that I was making, and it's over here it's basically a CSV parser that takes these rows and then turns them into chart rows into a list and holds their timestamp. And what it'll do is that it enqueues them into a queue so that they can go through a play queue method, which then spawns the notes as they come in like the order that they were added. In the game engine, they compete at the front of the queue to check whether the next row's timestamp have been reached in the queue and it hasn't. This is a natural fit because when you usually play a song, the playback is inherently sequential. The Rows are always consumed in order. When they're ran, the oldest fish no need to jump around or look at arbitrary positions. The first in, first out guarantee isn't just convenient, but it's actually the correct model for how the song plays. Because as they are added, they are just the ones oncoming from the parser right here.